Yeah.
Thank you for the opportunity from the M2FCT consortium. Very happy to be here to discuss with all of you about our project, real-time continuous monitoring of ionomer degradation of ion-sensitive field effect transistor microsensors. My name is Dongmei Dong. I'm the PI of the project. Together with me from our group are Dr. Shakhan Basali as the co-PI and our PhD student, Tinsley Benhaddouch. We are from Electrical and Computing Engineering Department, Florida International University. Let's start with the background. As the fuel cells move towards heavy-duty vehicles applications, the membrane durability becomes critically important. The chemical Tinsley, I'm not sure if I'm recording or no. Yes.
It is.
Okay.
You see
okay.
this blinking? Yeah.
Okay. The chemical degradation is the main concern, which arises from the peroxide formation and harmful radical attack. At the anode potential region, the atomic hydrogen is adsorbed on platinum. The oxygen crosses over the membrane from the cathode and gets reduced at the anode platinum catalyst to form the radical peroxide. And the presence of the impurities will even enhance the chemical degradation by reacting with the peroxides, producing hydroxyl and hydroperoxy radicals. And those radicals will attack the membrane, the backbone side chain, and end groups, causing the propagation and the polymer chain unzipping, and so on. The chemical degradation is also accompanied by the mechanical degradation, such as the membrane creep, micro crack, and the pinhole formation. According to previous research, this degradation will be accelerated at high temperatures from 80 to 120 Celsius degrees and low RH operations. As you may notice, the ionomer breakdown is accompanied by the release of several byproducts. Here we can make use of these signals and draw it as a signature of the membrane degradation. For instance, the fluoride ionine concentration can be used as an excellent signal reflecting the degradation of the ionomer. It is significantly important to address the ionomer degradation. A lot of efforts have been put into the materials approach so far. Meanwhile, it will be very helpful if we can monitor the ionomer degradation studies and quantify the degradation rates. Our collaborator, Tommy Rockwell's team at Landau has paid attention to this topic and researched on it. The current technology is using the equipment in the lab, Dynix ion chromatography system, to measure the fluoride concentration and to calculate the fluoride emission rate. As you can see here, the machine is about a mini fridge size. Our group has over 20 years research experience in the microsensors and integrated electronics. To leverage the research expertise at FIU, we are developing ion-sensitive field effect transistor electrochemical microsensors, which are miniaturized, portable, user-friendly, low cost, and can be functionalized for the fluoride detection. In year one, our project goal is to develop the operandal complementary characterizations to existing techniques for fuel cells. We will investigate the MOF hydrogel nanostructure to functionalize the sensing membrane for improved sensitivity and selectivity, and to probe the membrane degradation rates with increased temporal resolution. In year two is to employ AI deep learning architectures for sensor-based degradation prediction and predictive maintenance of fuel cells. Additionally, we are also exploring the additive manufacture of the microsensors for the mass production and mass adoption. For the impacts of our project, firstly, it will bring a miniaturized, user-friendly, specific diagnostics tool for fuel cell quantitative degradation analysis. Secondly, bridge the interdisciplinary research expertise across fuel cell membrane, integrated microelectronics, and computing analysis. Also, strengthen the collaboration of academic institutions, national labs, and industries. Another potential impact is to bring a new idea of integrating the microsensor design into the fuel cell vehicles. This comes from the user manual of the 2020 Honda Clarity. The indicator and the decision-making of changing the ion filter is based on the hours of the fuel cell vehicles covered. No specific monitoring or diagnostics tool has been integrated. We believe the success of our microsensor development will be of revolutionary contribution to the heavy-duty vehicle dynamic operating space in real driving. Next, I will leave the stage to our PhD student, Tinsley Benhaddouch.
Thank you, Dr. Dong. Hi, I'm Tinsley, and I will continue our discussion with collaboration opportunities and future engagements. At FIU, we have ongoing project Asterix, which is funded by DoE and NSA, INSIP, and among the partners and allies in this project are Tommy Rockwood and Courtney Queller from Los Alamos National Labs. We have also worked with Thomas Dodzinski from ORNL and Guido Bender from NREL to combine our efforts in submitting a new proposal. In the spirit of creating new collaborations, we truly look forward to meeting with you all and finding new avenues for mutually beneficial cooperation. To discuss the areas in which we would like to contribute to, firstly, to increase our knowledge in ionomer degradation, doing so by integrating microelectronic systems, sometimes referred to as lab on a chip. Also, by implementing advanced sensors with spatial and temporal probing diagnostics, and finally, with membrane degradation rate analysis. A second area of interest is to establish a parallel real and virtual fuel cell system with fuel cell modeling and analysis in the MATLAB Simulink, as well as predictive maintenance based on truth data sets. Overall, we are looking forward to contributing to fuel sustainability in the realms of hydrogen electrolysis, hydrogen storage, and CO2 redox reaction. Future work includes developing the fluoride anion sensor as a true fuel cell diagnostics tool, optimizing the functionalized sensing area with advanced nanostructures, MOF and hydrogel, and also by implementing additive manufacturing techniques. The video shown here is the current 3D printer at FIU facilities. It is limited in the access range and by the 10mm diameter of the nozzle. We are waiting on the arrival of the new 3D script, which has a 5 to 6 axis capability, and have also purchased a nozzle for increased resolution at a 10 nanometer scale. Other future work regarding modeling and analysis include designing a neural network-based predictive controller in the MATLAB and Simulink environment. We are here seeking for long-term commitments. We are M2FCT on board members for the next 2 years. And at the end of our project, we are open to continuing our work with the M2FCT consortium. Given that our facilities are not fully equipped for accelerated stress testing, we hope to work with the national labs to validate our machine learning algorithms for predictive maintenance with accelerated stress testing. We also look forward to working with industry partners on integration of microsensors into fuel cell vehicle design. And finally, to engage with the hydrogen research and development projects to develop the clean energy economy in the zero emission recycle loop. Thank you so much, and I will turn the stage back over to Dr. Dong.
Thank you, Tinsley. That's pretty much about our project overview. We are still pretty new to the M2FCT consortium, and to be frank, it's the first time for me to be the PI. So any suggestions, comments, questions or even any doubts from all of you will be very helpful for our project.